Hi friends, welcome back to the channel, and we are continuing on the series of lectures which addresses previous year questions which were asked in GATE from the topic of mechanical vibration. So for this particular video I have got two questions, 1 and 2 as shown over here. This is the first question. So the first question says a single degree of freedom system has a mass of m equal to 2 kg. So let me make then m is equal to 2 kg and stiffness k is 8 Newton per meter, and the viscous damping ratio, it is zeta not c. It is zeta, which is a fraction of c by cc. It is 0.02. They are asking me what is the dynamic magnification factor at an excitation frequency of 1.5 radians per second. So the excitation frequency is given by 1.5 radians per second. Take a moment and convince yourself that all units are consistent. Yes, they are all in SI, so you don't have to bother too much about the units. Now they are asking for the dynamic magnification factor. So we know the equation for dynamic magnification factor is modulus of x of I omega by the static deflection, which is f0 by k, is equal to 1 divided by root of 1 minus r square plus 2 zeta r whole square. So if you are wondering what are all these quantities, let me explain you with the help of a figure. Here I have shown a single degree of freedom system with stiffness K and with a damper C. Sorry, with it's a damper with the coefficient of viscous damping equal to Z. This little m is acted upon by an external harmonic force given by f0 e raised I omega t. I usually work with complex numbers, complex notation. You don't have to worry if it is f0 cos omega t, then you have to just take real part of f0 e raised I omega t and accordingly modify the response also. So the response will be the real part of whatever you are seeing over here. So everything is explained in my earlier videos. So when you have an excitation of this sort, the response is given like this. This is the amplitude of the response and this is the phase of the response. Amplitude of the response is given by the static deflection times the magnitude of the frequency response, which is given by this particular term over here, where r is the frequency ratio, the ratio of the excitation frequency to the natural frequency of the system, and zeta is the damping ratio, which is a fraction of the coefficient of viscous damping present in the system to the critical viscous damping coefficient of the system, which is 2 root km or 2 m omega n. Make sense? So this is the basic equation which is required to solve the problem. So they're asking us what is a dynamic magnification factor. Dynamic magnification factor is the fraction of these two things as shown here. Like the numerator denotes what is the amplitude of the response when you have an harmonic excitation, and the denominator shows the static deflection. Let's say I'm simply applying that f0, not that f0 is no longer harmonic, I'm just pulling the system by an amount f0. Then what would be the deflection in the system? It will be simply the force f0 divided by the stiffness of the spring. So that is the static deflection. So how much your response get magnified, that is given by this particular term, root of 1 minus r square whole square plus 2 zeta r whole square. Okay, so this is the equation. Now, so the inputs are given here: mass, stiffness, and the value for zeta, which is the damping ratio. Everything is given. So let me compute the frequency ratio first, which is omega by omega n. Omega n is root k by m, which is root of 8 by 2, which is 2, and my excitation frequency is 1.5 radians per second, that is also given. So r is 1.5 times 2, that is 3 by 4, that is 0.75. Am I right? Yes, I'm right. Yes, that's 0.75. So now you have values for r and zeta. It's simply plug and chug. You have the formula over here. One thing you should always remember, there is a square term here. Usually students miss this particular term and often end up with the wrong answer. So you have a value for r, you make sure you square it over here and then deduct that particular quantity from 1 and then take the square once again and add it to the rest of the terms as shown here. So once you do all this, you will get a dynamic magnification factor equal to 2.28. Makes sense? Now let's go ahead and try solving the next problem. In the next problem, they're actually asking us to compute the phase. So this question goes like this. You have a single degree of, this is the question I'm talking about. You have a single degree of freedom system with viscous damping. It is excited by a harmonic force. It is excited by a harmonic force, very important. It is excited by a harmonic force, and at resonance, they are asking what is the phase angle. So, in the earlier part of the video, I discussed all these things, all this formula, but I didn't mention about the phase. I told you the response is having an amplitude this much, and it is also harmonic with a frequency of omega, but it has a phase. So, what is a phase? What is the amount of phase? That is given by tan phi is equal to 2 zeta r divided by 1 minus r square. So this is the expression for phi, because if you want to completely define the response, then you should know the amplitude as well as the phase, because that's a basic concept of complex number. Okay, now they are saying it is at resonance. That means your r value is 1. That means tan phi will be assuming a value 2 zeta by 0, something like this. So you know that tan phi is defined like sin phi by cos phi. So if you take tan 90, then we will arrive at something like 1 by 0. This is not the right way to approach the problem, but I'm telling you, we have an expression where the denominator goes to 0 and the numerator is non-zero. Okay, so in that case corresponds more or less where phi is equal to 90, because when phi is equal to 90, tan phi is sin phi by cos phi, sin phi is 1 but cos phi is 0. So we have a similar scenario. That means for a damped single degree of freedom system undergoing, very important, it is undergoing a harmonic excitation. So in this particular scenario, the phase angle of the response will be 90 degrees. Makes sense? So it lags. Actually, the response lags by 90 degree with respect to the excitation. Thanks a lot for watching. One more thing before we wrap up. This phase is always 90 degree irrespective of the amount of damping present in the system. All curves, you draw multiple curves. When you plot phi versus r, you draw multiple curves like this, and for different zeta values, and all of these curves will, for r equal to 1, all of these curves will have a phi that will be equal to 90 degrees. So this is something useful which you can always keep in mind. Once again, thanks for watching.